Okay, so hello, my name's John Evans. In this video, what we're going to do is look at analysing multiple data sets, multiple powder diffraction patterns in TOPAS, or at least one way of analysing multiple data sets in TOPAS. So if you've looked at the previous videos, you know how to do a Rietveld refinement on an individual data set. But in real life, you may find you've got multiple data sets to analyse. You might have recorded powder diffraction patterns on your material as a function of time, or a function of temperature, or a function of evolving chemical environment. So you may find that you don't have one data set to analyse, you've got 10 data sets, or 100 data sets, or 1,000 data sets. Now you could analyse those individually using exactly the same methods we've looked at previously. But in practice, it's going to be useful to try and automate the process so that you can analyse the data more efficiently. So we're going to do that in this video, look at how to do that in this video using what's called sequential Rietveld analysis. And what I mean by sequential analysis is where you analyse an individual data set, and then you analyse the next data set, and the next data set, and the next data set, and you treat them all independently. There is a more specialized or a more powerful approach, which is called parametric Rietveld refinement. In a few specific cases, it can be a much more efficient way, much more sensible way of analyzing your diffraction data. And in a parametric fit, what you try and do is you fit a whole body of evolving diffraction data to a single evolving structural model. As I say, it's a bit of a specialist beast, and maybe in 5% of cases, it's the way that you need to analyze data. But in 95% of cases, this sequential approach that we'll look at today is probably the best thing to do. If you want some more information on sequential and parametric Rietveld refinement and how they differ, you can look at the textbook on the right. Or if you go to the TOPAS wiki and you do a search for the words sequential and parametric refinement, you'll find some notes comparing the two techniques. Okay, so what we're going to look at in this tutorial is how to modify a standard input file so that you can do this automated analysis of multiple data sets. We'll look at how you save the results of those analyses so that you can plot them easily afterwards. We'll look at a few little tricks in the input file to make your life easier when you do this type of analysis. We'll look at how to visualize multiple Rietveld fits in the TOPAS GUI, and then we'll look at how to plot your refined parameters using a Python script, which lets you very quickly see how all of the parameters are changing throughout the experiment that you're looking at. So you'll probably want the files downloaded to look at as we go through the tutorial. They should be all available from the web link that's by my laser pointer on the screen. Okay, so what are the key differences in an input file which allow you to do sequential analysis rather than just a single Rietveld analysis? Well, the two TOPAS instructions that you need to understand are the keyword numRuns and the keyword hash list. So when you're analyzing a series of data sets one after another, TOPAS calls each of those analyses a run. So if you want to analyze 3 different diffraction patterns, you tell TOPAS that the number of runs to do is 3. And then you need to feed it information for each of those individual runs, and that's done using the TOPAS hash list keyword. So you'll see in this input file segment here that I've defined a list, and that list contains items called file underscore name, temperature, and time. And so for each of the runs, I've got a list here of the data set that I want to analyze, the temperature of that data set, and the time. And I've done that for run number 0, run number 1, and run number 2. So TOPAS, when it's counting through runs, actually starts at 0. So if you've got 3 runs that you're doing, they're numbered 0, 1, and 2. And then later in the file, here's the section in the file xtd file name. Normally you would explicitly tell TOPAS the name of the file that you want to be analyzing. Here we've done something different. We're actually defining it in terms of a macro called file name. And the macro file name is actually defined by the parameter file underscore name for a given run number. So in the first run, TOPAS will go up here and it will pull out this file name, call that the value of the macro, and then that gets written into the xtd section. So it will change the file name that it's analyzing each time it steps through the list. And then the other thing you could do is it may be that some of the parameters from the experiment, some of the metadata, you actually want to use as part of your analysis. So I've got a little line here in the xtd section of the file which defines a parameter called TE, which is equal to the value of temperature, the second item in the list, for a given run number. So the first time you use this syntax, it'll be a little bit confusing, but you get used to it very, very quickly. One of the things that I tend to do is the parameters I define in my list, I normally give those capital names, capital letters at the start of the name, and then the parameters I use in the conventional part of the refinement, I use lowercase letters, and that helps me separate which ones are conventional parameters and which ones are coming from the list. The second way that you'll need to modify your input file is, as I said, you probably want to be saving the results of each analysis to an external file so that you can plot them easily at the end of the refinement. So this is TOPAS syntax for doing that. This line here says, I want you to append the results from each individual run to a file called results.txt. And what I want you to write in that file is I want you to write the file name of the dataset that we're analyzing. I want you to write the R factor at the end of the Rietveld refinement, the cell parameter of aluminium oxide, and the scale factor of aluminium oxide. So you would choose which parameters you want to output to this text file. And there's some little characters in pink on each of these lines which are specifying the output parameters. If you've done any coding, you'll realize what those little strings in pink are doing. If you haven't, what they are format instructions. They're telling TOPAS what format to output the data in. So a number, a string like percentage 11.5f, the f means write a float number, so a number like 1.2345. The 5 tells TOPAS how many numbers you want after the decimal place, and the 11 tells it how wide the number needs to be in total. Some of these output lines have got 2 of these strings here, and that's because when you're saving the results from TOPAS, you probably want to write out the parameter itself, but also the standard uncertainty on the parameter, the ESD, or the error on that parameter. So there's one format string for the parameter, and then the second format string for the ESD on that parameter. And then the final line here tells TOPAS to write a carriage return at the end of each line. So when it's analysed run number 1, it writes out a line of the input file. It puts a carriage return at the end. And so run number 2 is on a separate line. And you get a nice file for plotting in something like Excel or Python. Okay, so we're going to switch to JEdit and look at a real example. Just for some background, this is the example we're going to look at. These are some data from an experiment we were using to calibrate a hot air blower at a synchrotron. So it's one of these experiments where you have a sample in a capillary and you blow hot air on it to heat it up. And one of the issues with that type of experiment is you never know if the temperature of your capillary is exactly the same temperature that you set on your hot air blower. So one way around that is to do a calibration run. So that's what we did in this case. We took a mixture of aluminium oxide and silicon in a capillary, and we heated them from 30 degrees to 950 degrees. And the idea is because you know the thermal expansion of aluminium oxide and silicon, you know how the cell parameters ought to vary with temperature. If you extract these cell parameters from the data, you can see how different they are to what you expect, and therefore you can calibrate the true temperature of your sample. So in the experiment we did, we had 30 individual data sets which are stored in XYE files. We actually warmed the sample from 20 degrees to 400 degrees in 20 degree steps. And then after that, we did 50 degree steps up to 950 degrees centigrade. So these are the 30 data sets that we're going to analyze at the bottom of the screen here. So what we'll do next is we'll switch to JEdit and we'll try and do one of these sequential refinements. Okay, so here we are in JEdit. I've got open the file al203 underscore silicon underscore vt underscore 02.imp. And the input file is using the JEdit folding trick. So I've got 5 different sections of my input file folded away just for neatness. So let's have a look at what's in each of those sections of the input file. So the first section of the input file contains the overall information on the refinement. It contains, for example, the R factors for the fit, how many iterations to perform, when to say the refinement is converged. The second set of information in the file contains the key information about the hash list command that we've just discussed. If I open that section of the file up, you can see there's a section of the file where I've said I want to analyze 30 different data sets. I've defined a list, and in that list I've got the file name and the temperature for each of the individual powder diffraction patterns. So here's the file name of the first powder diffraction pattern, and here its temperature. So there are 30 of those listed all the way up to 950 centigrade. Actually, there's a little trick in my input file. I'm actually defining two lists in my input file. What I find in practice is I always want to analyze one or two of the data sets independently before I analyze all 30 of them. It lets you find errors in your input file before you analyze all of the data. So I've actually got a little line up here which says define a quantity called fit one test pattern. So if TOPAS has been told to fit one test pattern, it actually reads this list here. And this list just contains a single run, and it contains the file name and the temperature for an individual diffraction pattern. So if this quantity has been defined, TOPAS will analyze one data set. If it's not defined, so we comment it out, it will analyze all 30 of the data sets. And the main difference between the two sections is when you're analyzing multiple data sets, I've got one extra line in, which I've highlighted here. And that says to TOPAS at the end of the refinement, copy the output file to become the input file for the next analysis. So that way you can take the results from one refinement as the starting point for the next refinement. And that's what you'll nearly always want to do. If you want to always start from the same input file, you can just comment that line out. If you're analyzing just a single data set, you don't need that line in there, which is one of the reasons I have these two separate lists. So let's go back to just analyzing a single diffraction pattern to get us started in a minute. That's section 2 of the input file. Section 3 contains the normal information for a Rietveld analysis, the type of thing that we've looked at in earlier videos. So this is the name of the powder diffraction pattern. It's not named explicitly, but it comes from this macro called file name, which is itself defined from the list at the top of the file. And we've got the normal information about the starting and ending range of the Rietveld refinement, what the instrumental wavelength was, what kind of background function we're using, the normal type of things. Then it's a two-phase Rietveld refinement, so I've got a structural section for the aluminium oxide, all the normal type of parameters, but I've given them explicit names so that we can save them to a results file. That's the section for aluminium oxide. Here's the same information for silicon. And the only other difference to some of the input files we've looked at in videos before is because this is a synchrotron experiment, what I've actually done is I've analyzed a standard sample on the instrument, and I've used that to define an instrumental resolution function, so the expected peak shape for this particular diffractometer in this particular setup. So that instrumental peak shape is fed into each of the structural models, and then the structures themselves, I'm just refining a simple size and strain sample contribution to the peak shape. Okay, and then section 4 of our input file has got the output section. So just as we looked at in the other part of the video, this is the name of the results file that we're writing to, and these are all the parameters that I want to output to my results file. So that simple input file is all ready to do a Rietveld refinement. So if I send that across to TOPAS, and then I switch to TOPAS, I can use the play button to do my Rietveld analysis. And if I do that, I've analyzed my first diffraction pattern, and I get a nice fit to my first diffraction data set. So that suggests that the refinement is well set up to do the automated analysis. So let's just go back to TOPAS. There's one little thing that I forgot to tell you. Another little trick that I have in my input file is often when you're starting the process out and you want to test, say, the first data set in your diffraction pattern and then the last data set last diffraction pattern in your data set, you often want to make sure that your first refinement is properly converged, particularly when you're jumping from early in the experiment to late in the experiment. Your refinement may need a little bit of help to converge to the correct minimum. So actually in this general section of the input file, I have some special instructions that I tell TOPAS to do for the first analysis in the data series. The first analysis in the data series, if the run number is equal to 0, I actually make a separate backup on my input file just to make sure that if something goes wrong, I don't lose my carefully created input file. When you're doing this multiple analysis, what you'll often find is you analyze all of your data once, and then you decide to change your model, so you want to analyze the data again. The way that TOPAS writes to the results.txt file is it just appends the information at the bottom of the file. If you analyze your data multiple times, you'll end up with multiple sets of results in your output file. This line here gets around that problem. It says on the very first dataset that you analyze, delete any old file that's in the directory called results.txt, so you've got a clean file for writing to. And then the next line here says, well, actually, now open a new file called results.txt. And what I want you to do is at the top of the file, I want you to write some column headings. So when we come to plot the data in a moment, it's useful to have column headings at the top of each column, telling TOPAS what's being written out. And so these are the column headings that I'm going to need in results.txt. And then the final trick is, as I was saying, the first analysis that you do, it might be that your structural model isn't in the correct minimum. So in the very first analysis I do, I normally do some simple cycles of simulated annealing. So at the end of the first refinement, I actually want to do a continue after convergence. I randomize some of the parameters in the model, and I do 3 cycles of re-refinement to make sure that I'm in the correct minimum. Okay, so with that said, I think we're ready to analyze all of the diffraction data. So all we need to do is go back to our input file and comment out this line that says fit one test pattern, and then TOPAS will analyze all 30 of the diffraction patterns one after another. Let's try and get that to run so I can clear all of my refinements. I can click the play button, and TOPAS should do the first data set, and then the second, the third, and the fourth are all coming in one after another. If I press this little icon at the top here, this little triangle icon, you can see all the analysis coming through in a three-dimensional plot. So you can see each of these Rietvelds happening in real time. So in this case, it takes something like 20 seconds to analyze all 30 diffraction patterns, and here they are on the screen. So one of the nice things about TOPAS is it's got a great little view of visualizing multiple data sets. So I'm showing things in a kind of 3D view here. If I hold down the middle mouse button, I can drag around and I can see the 3D view in different formats. If I hold down the control key and I scroll across the surface, I can see each of these refinements one after another. Have a look at the quality of the refinement. I could zoom in and just look at a little section, the refinements. When you go into this 3D view, again using this sort of triangular shaped icon at the top, you get a little help menu, options menu plotting up, and that's got some nice little features for looking at multiple data sets. It might be that you just want to look at the difference plot to see where the problems are in your fit. So there's a little function here called diff only, which just shows the difference patterns. Or I can click it so that I see all of the diffraction data again. Quite often what you want to do is flick through the individual refinements one by one, and this button at the top here, the 2 little arrows, one to the left and one to the right, if you click with the right mouse button on that, you click through the patterns sequentially one after another so you can see the individual Rietveld fits. Let me just put the legend on because then it's easier to see. So if I go to chart options and then show the legend, what I've got in the screen here is the name of the dataset. This is dataset 464. And if I click with my right mouse button on the display next to previous icon, I go from experiment 464 to 465, 466, 467. You can flick through things very quickly. If I click on the left mouse button, I go backwards through the individual datasets. So that's one way of looking at the data. Another thing that's useful is you often just want to look at a little zoomed region of the data, so how individual peaks are fitting. The trouble with this next and previous pattern is as soon as you click on that, it resets the zoom level. So to stop that happening, what you can do is to zoom in on a small region of the diffraction pattern. And if, again, we go back to our help feature on the 2D options, if you click on help, there's a little dialog box that comes up that reminds you of some of the tricks that you can do. We're going to use this Shift 1, Shift 2 trick, which lets us flick through the patterns very, very quickly. In the second, we're going to use Shift Zoom and Shift Unzoom to just select certain data sets or to view all of the data sets. So the help menu reminds you of some of these little tricks. Okay, so what I'm going to do now on the keyboard is I'm holding down the Shift key and then I'm pressing number 1 on my keypad. And what we'll see is as I press number 1 once, twice, 3 times, 4 times, 5 times, I'm flicking through those individual Rietvelds one after another. If I click number 2, it goes backwards. I'm on 474, 473, 2, 1, 0. So what's often very useful is just to hold down Shift and 1, and then you can just flick through all of the refinements one after another very quickly and have a look at the quality of the fit. Okay, let me turn off the legend again just so the next pictures look a little bit prettier. And let me just redisplay all of the diffraction data. One thing that you'll often want to do is not look at all 30 of your diffraction patterns. The picture can get a little bit complicated. Let's imagine that I just want to look at a few diffraction patterns in the middle of my fit. If I hold down the Shift key and then I do a zoom, so I'm going to drag from the top left to the bottom right, that will just select the patterns that are in the rectangle that I've drawn. So now instead of there being 30 diffraction patterns, I'm now showing perhaps there are 10 diffraction patterns on the screen. If I just want to look at these 3, I can draw a little window around 3 of them. And again, I just see the 3 diffraction patterns I've selected. And if I unzoom, I see the full range of them. If you want to show all of the diffraction patterns again, you do what TOPAS calls an unzoom. I hold down the Shift key and I drag now from the bottom right to the top left, and all the diffraction patterns will appear again. So that's another quick feature. TOPAS has got some nice features for seeing the data a little bit more clearly. One thing you might want to do is turn off the calculated patterns. And TOPAS has color-coded these data sets with a sort of intensity rating. So the strong peaks are red and the weak parts of the pattern are blue. What you might want to do is look at the data in individual colors. So that just shows the diffraction patterns in different colors. But normally I go with the default view. Another feature is showing the diffraction surface. So if I click on Show Surface, then I can see the data as a kind of color-coded pseudo 3D map. And again, that can be a very quick way of visualizing the data, seeing where things are changing in the data set. And again, if I hold down the Control key, I can then scan across my surface and I can look at each of those individual plots. By holding the Shift key and moving the middle mouse button, you can see different sort of offsets of the diffraction data. Sometimes it's useful to lock the X offset, so just show a plot where 2 theta is running straight up the screen. So that's what I've done there. And now I can no longer drag these around. That's particularly useful when you want to show a plan view, which is a 2D picture of the diffraction data, so a pseudo film plot. And again, that can be a very useful way of looking at subtle changes in the diffraction data. So that's a 2D visualization of the same data on a square root scale or on a log scale. So that can be a really convenient way of seeing peaks appear and disappear during a variable temperature experiment, for example. So let me just go back to my default view and go back to a linear Y scale. So here's the view that we were looking at a few seconds ago. Lots of other kind of clever features that you can play with. One of the things that's nice to do is to go into this little color menu here. So TOPAS has got some beautiful little color rendering options for looking at the diffraction data in different ways. So you can show a contoured plot with orange contours. You can show a black and white contour plot of the data. I find this black and white plot quite convenient when you're wanting to look at individual fits. So now if I hold down the Control key and I scan across my data, you can see the individual Rietveld fits against this black and white background really quite nicely. There's some, let me go back to standard colors again. There's some rather garish features. There's a feature called Lava Run, which takes whatever color coding that you've got on your diffraction peaks and it trickles that down the diffraction data. Again, it seems a bit gimmicky, but sometimes that can be a useful way of seeing changes through the diffraction data, just watching these colors evolve on its surface. So that can be useful. Let me turn off the Lava Run and let me just go back to standard colors again. The other feature that can be useful is there's a feature called Cascade. So if I go to the options menu here, there's a feature called cascade scans. And what cascade scans does is when you activate it, it takes the pattern that's at the bottom of the screen and it puts it at the top of the screen. So if I run that, you'll see that what happens is you can see the diffraction data trickling down the screen towards you. And again, that can be a really useful way of spotting changes in your diffraction pattern. So for example, if I just zoom in on this little region here, you can see the data trickling down towards me. And again, if I hold down the control key on the first pattern, you can see the individual fits at the bottom of the diffraction data as the patterns cascade towards you. So again, it's a visualization trick, which can make it very convenient for spotting subtle changes in your diffraction pattern. So again, there's lots and lots of options in TOPAS for visualizing the diffraction data. So have a play with these various options. So let me turn the cascade off and reset things, and we're back to our standard picture. Good, so that's doing the refinement in TOPAS, that's visualizing the data in TOPAS. The final thing that you need to do with one of these sequential refinements is, of course, you need to look at the parameters that have come out of the refinement. So as I said, the results get written to a file called results.txt. The results.txt we can open up in JEdit, and it's just a simple text file which contains all of the parameters that we've just refined. So the first line of the file has got the column headings, which, if you remember, we wrote out from the input file. And then for each refinement, we've got the run number, the data set, the temperature, the R factor, the goodness of fit, the cell parameter, etc., etc. So it's a simple text file that you can then open up in any package you like for plotting. One little trick that I find really useful for these input files is when they get created, unless you've been very careful, the column heading names and the columns themselves don't line up perfectly. There's a nice little trick in JEdit just for fixing that problem, which lets you visualize these or read these files a little bit more easily. If I select all the data using Control-A, and then I go to macros, if you've used my instructions for setting up JEdit, you'll have a macro available called spaces multiple to single. And what that does is it looks for any tabs or multiple spaces in results.txt and it replaces them with a single space. So the file now looks like this and looks like that. Let me just turn off my speaker. And then if you select all the data and you do macro spaces align, you'll see that the column headings are now nicely lined up with the individual values. So it's very easy to read that file, and particularly to check if you've made any mistakes when you've labeled your columns. So that file looks beautiful to me. So let's just save that file. You don't have to do this step, but it can be useful. Then for plotting the data, as I say, you can use any plotting package you like. You could use Excel, you could use Origin. What I tend to use is, I use a little Python script because I find that's a very quick way of automatically visualizing all the data. So we can have a look at a little Python script which does that. Again, this is available on the tutorial webpage. If you're a Python person, it will be completely straightforward to you. If not, let's just have a quick look at this Python script so you know how it works. So it's a very simple script. It's only something like 25 lines long. And in this script, there's a few lines you need to know something about. This line here says import the Python plotting library, which is called matplotlib. That's what tells Python how to create graphs. The next line says import what's called the pandas library. And pandas, if you like, is Excel or Python. It lets Python manipulate data files in the same way that you might do in Excel. Then if you want to use this file, all you need to do is change the name of your results file in this line here. This is a line that says, use pandas to read the results from results.txt and store them in an internal data file called df. And then you just need to tell the routine which column you want to plot on your x-axis, what you want as the x-axis when you create the plots. So in our case, we're going to plot everything against the column that's labeled temperature. And then there's a very simple section in the Python script which basically looks through the data file that we've read in and it runs through each of the columns in turn and decides if it wants to make a plot of that column. So it says for each of the things which we'll call Y column in the data file, do a few things. The first thing that the script does is it tries to read the name of the next column over. So when we're trying to decide whether we want to plot ESDs on a column or not, what the script does is it looks at an individual column. It looks at the column one to the right of that and sees if it's got a label ESD or error. If it has, it knows, well, that column has got an error associated with them. If it doesn't find a column, it just says, calls that particular variable none. And then here's the little loop that does all of the hard work for us. It basically says, if the Y column doesn't have the same name as X column, and it's not labeled as being an ESD or an error, then you want to plot that column. So obviously, if the Y column and the X column name are the same, you don't want to plot it. You don't want to plot temperature against temperature. And we probably don't want to be plotting the individual ESD columns. So as long as the Y column is not an ESD and it's not the same as the X column, you create a figure of a certain size, you set a label on the X-axis, you set a label on the Y-axis, you give the window a title, a sensible title, and then you plot the data. If the next column over is called either ESD or contains the string error, then put some error bars on top of the plot, and then at the end show all of the plots so that we can look at them. So it's only something like 25 lines of Python, and if you want to use this script, all you need to do is change the name of the file you're plotting and the name of the X column if it's different. We can just run that little script. So if I just go to a DOS command window and look, I'm in the right directory where that script is sitting. So on my computer, I can just type python plot_all.py return, and then Python will go away. It will set itself up by reading in the different libraries. It will create all 20 plots. It will put the error bars on them, and then it will throw them up on the screen. So you can see on the screen here, here's a plot of my 0 offset coefficient, so the 2 theta 0 point error on the diffractometer as a function of temperature, and I've got a nice plot with all of the error bars shown. Behind that here I've got a plot of, this is the B value, the temperature value on silicon as a function of temperature, and it increases nicely with temperature. Here's the plot of the temperature factor on the aluminium oxide as a function of temperature. So all of these windows have been created, and they've got nice little labels so we can just look at them one by one. The silicon cell parameter is the quantity that we're probably interested in this experiment. We were trying to calibrate the diffractometer, so we wanted to know the thermal expansion of silicon to compare to the literature, and we can see that the silicon cell parameter is nicely defined. One of the key things you want to look at is the quality of the refinements when you're doing this kind of variable temperature work or this multiple sequential analysis. So it's really important to look, for example, at the R factor of the refinement as a function of temperature, or the goodness of fit as a function of temperature. So here's the goodness of fit. It varies between about 1.5 and 1.46 over the range of the experiment. And one of the nice things about these little Python windows is, as compared to something like Excel, is they've got a little bit of functionality. So, if you want to zoom in on a region, you can do that in these windows. You can change the appearance of the plot if you want to. I mean, it looks like this goodness of fit is changing quite significantly through the experiment, but if I replot that on a y-axis scale of say 0 to 3 and apply that, you can see that in fact the goodness of fit is more or less constant throughout this analysis. So we've got equal confidence in all of these refinements. So I hope that the trick that we've looked at, setting up an input file to do multiple analysis in TOPAS, visualizing the results in TOPAS itself, and then plotting the results using these little Python tricks will greatly speed up the way that you can do these multiple sequential analysis. So I hope that's been useful. All of the files that you need, as I say, are going to be on the tutorial page, which was linked at the beginning of the video. And if you look on the wiki, there are some background notes which take you through some of the more theoretical side of this and some of the tips and tricks for doing this type of analysis properly. So as I say, I hope that's been useful, and we'll explore more things in later videos. Bye for now.